Hi, this session is about the stability theorem. This is an important theorem in topological data analysis. In a sense, it's the theorem that makes all of the data analysis work. And you'll see when we get to the end, see what it's good for. Okay, we're going to be working with a special case, working with continuous functions. And we're going to be looking at sub-level sets of continuous functions. So let's start with an example. So here's a continuous function defined on the real line, and we can see it has a number of local maxima and local minima. We're going to be interested in sublevel sets. So that means for a value a on the y-axis, we're going to look at the set xa, which is a set of all x in R, so that f of x is less than or equal to a. Right? So here we see for a3, the value I picked here, we get two connected components on the x-axis. And I also have other values of a here. We're going to use these to define a filtration. So let's see how that's done. So if we have an increasing sequence of function values, say a1, a2, and so on, up to an, we get a collection of subsets of the domain xa1, xa2, all the way up to xan. And we're going to look at connected components, so dimension 0, persistent homology. And we can watch the formation and merging of connected components as we go. Let's go to the next slide. Okay, so here we see the same function, the graph, 6 different versions of it. In each case, we have an a value marked. These are the same a values I showed on the original slide. So now on the upper left, we have a single value a1, and you notice there's a single connected component, which is the half-infinite axis to the left of that point where xa1 is located. Okay, now, in the second figure, we have a larger value of a2. We see 2 connected components. The original one has grown a little bit, and now we see a new one form around the local minimum. We increase the value to a3. At a3, we move past the local maximum. Here's the local max. We move past that. So that means the 2 connected components we saw in figure 2 have joined. At the same time, a3 is high enough that we pick up a little bit of the region around the local minimum here to the right. That gives us a new connected component, a small but a new one on the x-axis. We move to a4, and xa4, and we see another connected component form. We've increased the value enough that we pick up this second local minimum, and no components have joined, so we get 3. Now we go up to a5 and look at xa5, and here we see the 2 components on the right have joined. We added this local maximum, so these local minima have joined. We still have 2 connected components. We go to a6. a6 gets us past this local maximum, and both of the large connected components have joined, and we see a single connected component. So we can see the progression, the addition of connected components, and then the merging of connected components here. Okay, now we want to look at a barcode for this. So here we have a barcode. You see it has 4 bars for the 4 different connected components that we see over the course of the filtration. We have the large one starting at a1, and it persists all the way to the end at a6. We see the shorter bar starting at a2, which disappeared at a3. That one merged with the first bar. At a3, we see another bar form that lasts till a4 here and keeps going. At a4, we see a short bar form. It dies at a5, and it joins the bar. It keeps going to a6. But that's third bar from the bottom. That dies at a6, and we have 1 connected component left at the end. Well, these 4 bars give us 4 persistence points in the persistence diagram on the right. We see the bar A1 starting at A1 going to A6, so the coordinates are A1, A6. That's the big bar. Then we have A2, A3. That's the next bar. It's a little bit shorter. Then we see the bar A3, A6. That persists till A6 and then dies. And then we have this short bar, which started at A4 and goes to A5. That gives us this persistence point close to the diagonal. So we see 4 bars. Here's the translation into 4 persistence points in a persistence diagram. Okay, now here we want to do something new. You see on the left, I've taken the original function and I've added some small bumps to it. Here on the left, here in the middle, and here at this local minimum on the right. So everywhere else, let's assume the function is the same. At those spots, I've perturbed the function to create a new function, g of x, which differs by the original function by some small value, say epsilon. Those differences in the y values are no larger than epsilon. Well, we can create a barcode and a persistence diagram associated with a filtration for the blue curve, the function g. Now, g has the same four persistence points we saw before. We didn't alter the major features of the local minima and local maxima. The perturbations we added, though, are very small, so that means they appear at a certain a value, appear in a certain sublevel set, and then we increase the a value slightly, and they disappear. So those features, those bars, are very short-lived. So their persistence points are close to the diagonal. And here we see the three locations where we would see the effect of the perturbation. So now let's consider P to be the original red persistence points and Q to be red and blue. So P in red, that's for F, Q in red and blue, that's for G. Now we want to look at the bottleneck distance between them. Since they have the 4 points in common in red, that contributes nothing to the calculation of the bottleneck distance. The pairing gives us 0 distance between them. On the other hand, we have these 3 new points we see along the diagonal. They're unpaired to any of the persistence points for F in red, so we pair them with the diagonal, but they're very close to the diagonal. In fact, they're less than epsilon away from the diagonal. So that means if we look at the bottleneck distance between P for F and Q for G, it's less than epsilon. Okay? So this is really the statement of the stability theorem. So let's look at that. Okay, so the stability theorem, here's a version of it for metric spaces. There are different versions. Let X be a metric space that admits a simplicial structure. So we didn't build a simplicial structure in the real line, but we could have. Okay, if F and G are continuous functions from X to R, which have some nice properties, so a finite number of critical points, for example, and they're functions such that the difference between them, so this is measured along the y-axis in the y direction, if that is always less than epsilon, then if we use the sublevel sets to create a persistence, a filtration, and then a persistence diagram, those diagrams will have bottleneck distance less than epsilon apart. This is the stability theorem. There are different versions of this for different contexts, but they all have the same effect. That if the data that we use to create the persistence diagram is perturbed a small amount, the diagrams will change only by a small amount. You can think of this as something like a continuity theorem from data to persistence diagrams. And that's the end of this session. Thank you.